Hello, welcome to this new video from Guidancee Education channel. This is for class 12 physics. We are discussing chapter 1, charges and fields. Under that we are discussing electric dipole. Let us see the subtopics that are discussed. The subtopics discussed are effect of external uniform two-dimensional electric field on electric dipole resting at an angle to it, derivation of formula for torque on the dipole, demonstration of direction of torque, a small additional video. This will be of great use to you, so watch the video completely without skipping, and if you think the video is useful, do like the video, share the video, and also leave your doubts or comments in the comment box below. If you have not yet subscribed my channel, do subscribe it now and also press the bell button so that you get intimated as soon as videos are posted. Thank you very much. Come, let us see the video. Electric dipole in two-dimensional uniform external electric field. We have already discussed electric dipole and field due to electric dipole. Electric dipole itself has an electric field. But in this video, we are going to discuss what happens when an electric dipole is placed in an uniform external electric field. The electric dipole with central point O is resting at an angle in the uniform external electric field, and AB is the dipole moment direction. This is the uniform electric field representation. Its direction is shown by the arrowhead. The electric field direction and the direction of the dipole moment bear an angle theta. The external electric field exerts a force on negative Q and also at a positive Q. Electrostatic force is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Electric field is equal to 1 by 4 pi epsilon naught Q by R square. So we get another expression for F equal to QE. So negative Q experiences a force equal to negative QE and positive Q experiences a force QE. Direction of negative QE is opposite to direction of electric field, and the direction of QE is in the same direction as that of direction of electric field. So here you have two forces at the two ends A and B acting in opposite direction. It forms a couple. Couple causes the turning effect of force called torque, represented by the letter tau. So a dipole resting at an angle to the uniform electric field experiences a turning force, or it rotates. These arrows show the direction of the turning, that is in anti-clockwise direction. The dipole rotates and then aligns itself with the direction of the electric field. They are in same direction. This turning force is called torque. Torque is a vector quantity. It has magnitude and direction. We will use this diagram. Let this point be marked as C. AC is the distance between the two forces. The two forces form a couple, so AC is the arm of the couple. Now we will derive an expression for torque. AB is equal to axis of the dipole equal to 2A. Dipole rests at an angle theta. Angle ABC is equal to theta. If this angle is theta, this angle also has to be theta. So AC is equal to AB sin theta. The effectiveness of the couple is given by the term moment of couple. Just like dipole moment, moment of couple is equal to force into the distance separating the two forces. That is F into AC, but AC is equal to AB sin theta. So the equation becomes F into AB sin theta, but AB is equal to 2A, so it becomes F into 2A sin theta. Substituting for F and rearranging, you get torque is equal to Q2A E sin theta. But we know Q2A is equal to dipole moment P. So the expression becomes PE sin theta. So torque is equal to PE sin theta. So if three quantities are known, that is P, external electric field, and the angle between electric field and dipole, then it can be calculated. For the same value of P and external electric field, torque depends on the angle in which it is aligned. How can we write it in the vector form? P is a vector. So also E is a vector. So torque also is vector. So we have to find the cross product of P and E. So the vector form is torque vector is equal to P vector cross E vector. So these are the expressions for torque. Now the direction of torque. Electric field direction is planar, it is in 2 dimension. So also the dipole is resting in 2 dimension at an angle. The torque direction will be perpendicular to both these vectors. That is, it may be directed into the plane of paper or it may project from the plane of paper. Direction of torque can be determined by right hand rule or right hand screw rule. Watch this video that I have included in this video. In this video, I shall demonstrate the movement of the electric dipole kept at an angle in a uniform electric field and also demonstrate the direction of torque experienced by the electric dipole. I have already prepared a diagram here. This is the direction of the electric field. This is the direction of the dipole moment P. Negative Q is at this end and positive Q is at this end. This is the midpoint of the electric dipole marked O. Torque is a vector and it is a cross product of dipole moment and electric field. In the case of cross product, P cross E is not equal to E cross P. So we have to be very careful in that matter. Direction of torque can be determined by either of the two rules that are given here. That is right hand rule or right hand thumb rule and right hand screw rule. These two rules find application in various topics where cross product is involved. Our present context is torque on electric dipole. I will first demonstrate how right hand rule is applied in this case. The right palm is kept on the first vector along the little finger. This is the first vector P. So it is placed on that along the little finger. The fingers are then curled towards the second vector, that is towards the direction of the electric field. This is the direction in which the dipole will rotate to align itself with the direction of the electric field. The direction is anti-clockwise. It is a single word, anti-clockwise. What is the direction of the thumb when the fingers are curled in this fashion? It is directing upward, projecting out from the plane of paper. Here the angle is theta, the small angle. It is resting at an angle theta. The outer angle is not considered, it is a bigger angle. It is the inner angle that is considered. This diagram shows another case. The electric field is reverse, that is directed downward, that is the electric field, and the dipole is resting in the original position with dipole moment in the same direction. This is negative Q, this is positive Q. The two vectors are at an angle theta. Now the dipole rotates in the clockwise direction in order to align with the electric field. To apply right hand rule in this case, we keep the right hand palm along the forefinger or along the first finger, that is pointing finger, and curl the fingers towards the electric field direction, that is clockwise direction. You can see that the thumb points into the plane of paper. This is the plane of paper, torque points into that. If the fingers are curled in the anti-clockwise direction, torque is projecting from the plane of paper. Now let us apply the right hand screw rule. You are familiar with this right hand screw. This is the head of the screw. To fix an object, the screw is turned in the clockwise direction. Then the screw slowly moves downward. When the screw is turned in the anti-clockwise direction, it slowly moves upward. The same principle applies in opening and closing a bottle. I have a small bottle here. This is the lid of the bottle. We turn the lid in the anti-clockwise direction in order to open the bottle. To close the bottle, we have to move the lid in the downward direction. For that, we turn the lid in the clockwise direction and it moves down. We know all this from practical life. Now, using these matchsticks, I will just demonstrate how the dipole rotates in uniform external electric field. Let this end represent the direction of the vectors. One matchstick is placed on the electric field direction and the other on the dipole moment direction. The initial angle between them is theta. Because of the torque, the dipole automatically rotates in the anti-clockwise direction and the angle between the two becomes equal to 0. Now in the other case, this is the electric field and this is the direction of the dipole moment. This is the angle theta between them. The outer angle, larger angle, is not considered. Now the dipole rotates in the clockwise direction and aligns with the electric field direction. Now the angle between the two is equal to 0. So this is how the electric dipole rotates when kept in uniform electric field. But the direction of the torque, in the case of anti-clockwise movement, it is upward. In the case of clockwise motion, it is directed downward. This is a very simple concept, but some children find it very difficult to understand this. That is why I took so much pain and interest to make this small video and attach that with the main video. If you think the video is useful, like the video, share the video and also leave your comments in the comment box below. Please subscribe my channel and also press the bell button for notification. Thank you. We will now see the statements of the two rules. The right hand screw rule and right hand rule that I have given here is just for the sake of understanding the direction of torque experienced by an electric dipole in a uniform electric field. You need not learn this by heart. When we start electricity and magnetism, I will give you the statement which you can learn by heart. And if at all a question comes, you can then give that as answer. The right hand screw rule states that in vector product, that is cross product, the direction of the product is in the direction of the movement of the right hand screw in the upward or downward direction when the screw is rotated in the anti-clockwise or clockwise direction respectively. Right hand rule. In vector product, when the right hand palm is placed on the first vector and fingers are curled towards the second vector, the direction of the product is given by the direction of the thumb. That's all. Thank you very much. We will meet in the next video with another important topic. Till then, bye. Take care. Okay.